Welcome to this class. Now we will continue EB evaporation. So in last class what we have learned? We have learned about thermal evaporation and its limitation as well. So in the EB evaporation, how we overcome the limitation of thermal evaporation. So if you recall, right, in thermal evaporation the limitation was that when you heat the material, so that the source material, if the melting point of the source material is more than the melting point of the source holder, then we cannot use thermal evaporation, because the source holder will melt first before the material itself. So, how to overcome that particular limitation? Then the answer to that limitation or overcoming the limitation is electron beam evaporation. So, if you see the slide, right, what you will see is that let us understand this particular schematic. Before we go to this schematic, first understand E beam evaporation or electron beam evaporation is a physical vapor deposition process that allows the user to evaporate materials that are difficult or even impossible to process using standard resistive thermal evaporation, right. That is first thing, and we said that why, how it will be useful and how it works is a second question. But first thing is that the role of E beam is that it can deposit materials that are difficult to deposit using thermal evaporation, one thing. Okay. Some of these materials include high temperature materials and some ceramics. We also understand this thing because those melting point of those materials would be extremely high. Now, how this works, right. So, let us understand this particular figure. I will say figure 1 like this. Okay. So, what you see here is that there is a source holder which we call crucible, CRUCIBLE, crucible. Okay. Then there is source, right. So, this here, this is source. Okay. Then we have here in the back side we cool the crucible, alright, because it gets too heated up. Now, how the electrons are generated? So, from the filament the electron beam is generated, and this beam is accelerated by the accelerating electrode. So, this is a filament, right. I will say F, the electrons are generated and electron beam is further accelerated with the help of accelerating electrode AE. Okay. So, you can see here the electron beam, right, that is generated and accelerated. Once it accelerates, there is a deflecting magnets. This deflecting magnets will deflect the E beam, and the E beam will get incident on the source which is loaded into the crucible or onto the crucible, right. So, the electron from the filament travels to accelerating electrodes through and bends through the help of magnetic field or deflecting magnet, and then it gets incident on the source. When it is incident on the source will start heating and melting, and that is why you heard it, we can see here something written molten source, molten source. Okay. And then you know when the source melts, what will happen? It will start evaporating. When it is evaporating, what will happen? It will start depositing onto the substrate. So, either you can have point source or you can sweep this electron beam, right, in a raster scanning mechanism or in a triangular form mechanism. So, there are different ways of controlling this electron beam, but the idea is that in this case the E beam will be used to heat the source that is loaded onto the crucible, and when it melts it gets deposited. You can see here the shield, you can see here. So, let me just erase the other things. So, the circle that is left here is the shield that we were talking about, correct. Now, this shield will protect or not allow the material that gets evaporated through here, because this shield here, right, will block the material has given off. So, we have to remove the shield from the path, so deposition starts. Before deposition starts, what is important, that the source is melted properly. Now, here you can see the source loaded onto the source holder or crucible, right. The source is loaded onto the crucible and the electron beam is generated. It comes from the bottom, from here, and it gets deposited like this, right. It is incident on this source. Okay. So, this comes from this and then bends it here, and you can see the E beam. Okay. So, the same thing is written more or less here, is that the to generate the electron beam, and electrical current is applied to a filament which is subject to a high electric field. This field causes the electrons in the filament to escape and accelerate away. The electrons are focused by magnets to form a beam which is directed towards a crucible that contains the materials or a source, and the energy of electron beam is transferred to the material to start evaporation. Many materials will either melt or evaporate or sublimate. So, you can see here there is a deposition monitor, right. You can see very clearly what is it, is a QCM. We talked about quartz crystal monitor, right. People use different terms, we said deposition monitor, fine. There is a electron beam filament, there is a electrical supply, there is a hearth, there is a water cooling, and you can see that the crucible is loaded here, and then E beam will come and is directed towards the source in the crucible, so that it melts and start evaporating. So, now if you understand a bit more, thermal evaporation suffers from contamination by evaporation of the crucible materials, and this process is not efficient to evaporate high melting point materials. But E beam evaporation in contrast is used to overcome these problems. It uses water cooled crucible or in the depression of a water cooled copper hearth. The electrons are thermoionically emitted from heated filaments that we have seen in the last slide, right, and are shielded from direct line of sight of the evaporant charge and substrate. The filament cathode assembly potential is biased negatively with respect to the grounded anode to accelerate the electrons, which we can understand very easily. And finally, the magnetic field is generated by the deflecting magnets, and the electron is deflected in a 270 degree circular arc, and then it is focused onto the earth and evaporant charge at ground potential. This is a video that will help you to understand the E beam evaporation. So, let me play the video. So, now what are the power requirements? So, the power requirements for E beam evaporation is approximately 10 kilowatt per centimeter square, and dielectric requires only 1 to 2 kilowatts per centimeter square. The contamination level of deposited film using E beam evaporation is less than other PVD methods. Very important to understand that the E beam evaporation contaminates comparatively lesser than other PVD methods. The electron density leaving the hot filament due to thermoionic emission, right, can be expressed by Richardson equation, which is given in here, right, and if where A is what, Richardson constant, Q is in coulombs, and then we have work function of the material as well. So, near to evaporant surface, evaporant flux shows a laminar flow. There is a laminar and turbulent flow, right. So, laminar flow is a smooth flow, turbulent flow is uneven flow, right, turbulent flow. So, let me give an example. If you ever taken a flight, right, you may have experienced turbulence. Okay, forget about the flight. If the river is calm, right, it's smoothly flowing, versus river which is flowing during the monsoons, right. So, that is turbulent, all right, in nature, while smooth river is a laminar. In just giving a very kind of simple example, so that most of you understand. Okay. So, the turbulence versus laminar. So, in the evaporant near to the evaporant surface, the evaporant flux shows a laminar flow, and uniformity of thickness can be described with the help of the cosine law, right. So, in the case of the E beam evaporation, how uniform the deposition will be there, it can be based on the cosine law. Now, let us understand different kind of evaporation sources. So, one is single pocket, one is rotary pocket, and finally, third one is a linear pocket. So, what is the single pocket versus rotary pocket versus linear pocket? So, a water cooled copper block is bored out to have a pocket, which is right now you can see here, right, in shape of an inverted truncated cone, is not it. Now, source material is placed within this pocket. So, within this particular pocket the crucible is placed, right, and then or the source material is placed or within the crucible whose exterior fits squarely within this pocket. So, you can have a crucible and then that crucible fits here, and within the crucible, so crucible is like this, right, and then within the crucible you can load the material. The crucible has smaller similar pocket within it. A magnetic structure consisting of permanent magnet and 2 pole extensions are located around the block such that the field lines up parallelly to one side of the block, right, and the E beam will come here and will incident or directed here. On the same side of the block below these primary fields lines is a filament which produce electron by thermionic emissions and is formed into a beam, which we already know. It forms 270-degree arc, which we already know. An additional electromagnetic coil known as sweep coil, this is important, sweep coil is employed to effectively raster the beam around the surface of the contents of the pocket to evenly hit the source material, because continuously if you point, use a point source, like say this is a crucible, right, and then you use only electron beam in the center like a point source, then what will happen, that the other material will not get deposited, only that area which is where the electron is focused, that will get deposited. So, have a uniform deposition and uniform melting of the material, we can use a raster beam, but for raster beam we have to have a sweep coil. So, sweep coil is also employed to effectively use the raster scanning, and that will evenly hit the source, which is a part of the operation and typically referred to as XY sweeping. As I told you that there are different kind of sweeping methods, and we can use a control program for the electromagnetic coil. Materials with lower melting points melt readily within and fill the crucible, and they do not require XY sweep. So, for example, if I deposit aluminum with EB evaporation, I do not require XY sweep, but there is a material which is having a higher melting point, you require a XY sweep. Materials with high melting point require XY sweep. So, to prevent the E beam from boring a hole into the metal and subsequently spitting, which creates large modules of the source material in growing thin film, which is undesirable. That means, if you continuously point only electron beam in one area, then it will create a hole, and a bigger chunk of the material will be melted and faster, such that in the thin film, instead of having a uniform grains, right, which are the atoms in a way, that you will find a larger modules, which is not desirable. Now, this is only for one source. What if I want to deposit multiple source, and that is why we have a rotary pocket and we have a linear pocket. As you can see in the rotary pocket, the other crucibles are shielded by this particular shield. Okay, it is behind that, the circle that I have written drawn here, no, it is behind the shield, okay, or below the shield, in a right way is below the shield. So, whichever material you want to deposit, you just bring that one into the site of the electron beam. So, first if this is the material yet you want to deposit, you can open this one and all the other would be shielded by the shield. Then you rotate this one and bring the another material or the source holder or the crucible in the site of the electron beam. So, you can rotate it, well, because you can rotate different blocks, right, or pockets, it is called rotary pocket mechanism. A rotary pocket electron beam source has all the same paths as single pocket unit, except that the water cooled copper block is a turret of multiple pockets, each of which can be indexed into a position. With this design, a number of different materials can be evaporated sequentially from a common magnet emitter sweep coil structure, right. Obviously, these include additional shielding to prevent cross contamination, which is here. Like I said, this is a shield, right, and the pocket position is chosen via motorized or rotary indexer. So, what happens is the linear one. Linear one also has 4, 1, 2, 3 and 4, whichever you want, you just bring it here. Okay. This is where the electron beam would be there. So, you can bring first, second, third or fourth, right, pocket in the site of the electron beam. A linear pocket electron beam source is similar to rotary pocket source, except the pockets are arranged in a line and are indexed into position in a linear fashion with common magnet emitter sweep coil structures. Got it? So, there are electron beam evaporation sources, as you can see in this particular slide. Okay. We will stop here. In the next class, we will talk about another PVD technique, which we call as a sputtering. So, thermal evaporation, E-beam evaporation, and third one is sputtering. Okay. So, till then you take care. I will see you in next class.